And now we are discussing about optoelectronic devices. Until now, we have discussed about electronic devices. All these electronic devices we have discussed, majoritarily we have conveyed a message that we are concentrating on the semiconductor physics. Based on how the semiconductor material is behaving, depending upon that, the property of our electronic device is varying. We have discussed various electronic devices, but in this chapter, we are going to discuss about the optoelectronic devices. Here we will try to understand how the light will affect our electronic device, how the light will affect different electronic components. Light may be either visible light, we have ultraviolet light or infrared light. In the spectrum, we have categorized light into visible light, means which we are seeing, whatever the colors you are seeing, whether you are seeing the board, because the light is falling on your eye and it is going to retina, and then finally you are observing this. That particular signal is going through the optical nerve to the brain and it is indicating I am holding a chalk piece. This chalk piece color is white. If the light is not there, I am not able to see this chalk piece. If light is not there, we are not able to see any object around us. So light is essential to us to see any object. Our eyes completely depend on the light. Similarly, the electronic components which we are discussing now, they also depend on the light. The first electronic component we are discussing, it is light dependent resistor. As the name indicates, this resistor depends on the light. If the light is varying, the resistance varies. Whenever the light falls more on this resistor, the resistance decreases. Whenever the falling light is not observed on the resistor, then the resistance is less. So it is a variable resistor. It is a variable resistor and its resistance varies with respect to the light. When the light intensity is more, then the resistance is decreasing. When the light intensity is less, then we observe the resistance is more. So this resistance is being operated by the light. That's why we are calling this as light dependent resistor, where we use this light dependent resistor. Example, normally when you come across your streets, sometimes when it becomes 7 o'clock in the morning, still you will observe some lights are in on condition. We don't want lights in the sunlight time. Example, at 7 o'clock or 8 o'clock, maybe they forgot to turn off that light. So we want to avoid the power wastage. In the automatic street lights, when the sunlight comes, we want the public street light should be turned off automatically. When the sunlight enters, all the lights we see in the parks, we want them to turn off automatically. Automatically means there is no need of the human intervention. There is no need for me to go to the switchboard and to turn off the light. Because it is a tedious task. It is a difficult task. Because the human error may be occurred. Maybe we can forget a particular light. Because of that, there will be a power wastage. So to avoid that, we want a system in which when the sunlight comes, the light should turn off automatically. In the automatic street lights. In the automatic street lights, we use this LDR. When the light falls, then the resistance decreases. Automatically, it will give an indication that you have to turn off that. By using a transistor, which we have already discussed, we can design a simple electronic circuit by using the LDR and transistor for the automatic street light. And we also use in light intensity meters. Whenever we want to measure the intensity of a light, then also we can use the LDR. LDR will give, this is the intensity of the light. How the LDR is giving, sir, how the LDR will come to know about the light intensity. LDR will not give the light intensity directly in the illumination, but LDR indicates when the light intensity is more, then the resistance is less. Because the resistance is less, we can interpret, okay, light intensity is more. Based on the decrement of the resistance in the light intensity meter, we can interpret particularly there is a possibility for the more intensity of the light. That's how the light meters will work. So light meters, they use the LDR. There are many applications, like sometimes when we want to operate the camera, every time the lighting environment might not be in our hands. Sometimes sunlight may come with the extra light effect. Sometimes we do not observe the much sunlight. So, but our camera settings, generally they will be in static mode. But in modern day times, the cameras are coming with the automatic setting effects. There also, we are using this automatic changing, like depending upon the light. If the external light is more, there is no need for my camera to give more light. If the external light is less, like when we are taking a photograph in the night time, then we require an additional light from our camera to capture a particular image. So in those times, we generally, for making the light to be adjusted according to my need, there we use the LDR. And in burglar alarms, in a particular industry or in a particular place, we don't want the light to be dominated more than this range. At that time, the alarm will ring. And similarly, outdoor signage. When we are going in the night time, if we do not see the signage board, accidents may occur automatically. So the signage board should be visibly appear to us from a distant place. So light should be adjusted accordingly such that we can see some signage boards accordingly even we are far away from that board. So these are the applications of the LDR. As we discussed, it is a passive component. It does not store any energy. It is a resistor, but it is a variable resistor, and we are calling that as a light dependent resistor. And what material we use for the construction of this resistor, sir? We are using semiconductor material. Why semiconductor? Here, we are trying to use the properties of the semiconductor material. Example, I am using cadmium sulfate. This cadmium sulfate is a photosensitive material, means it will capture the light. It will take the light. Example, after taking the light in this cadmium sulfate, which is a semiconductor material, the electrons in the last orbit, they will come out and these electrons will become free electrons. When the light falls on this photosensitive material, this is the photosensitive material. When the light falls on this photosensitive material, then the electrons in the last orbit of the atom, they will come out. Why they have come out? Because these electrons, they gained the energy. When the electrons gain energy, they come out of the orbit because this is the last orbit. They are coming out of the atom. These electrons are called as free electrons. They are not influenced by any nuclear forces. They are not influenced by any force from the protons, from the nucleus. These electrons are called as free electrons. Why the electrons in the valence band, or why the electrons in the last orbit, or why the electrons in the valence orbit, they have come out? Because they gained the energy. How they got the energy? Light itself, it is the energy. Light is having particle nature and light is also having the wave nature. You know, Newton came and he mentioned, I have discovered light is having particle nature. And then Christian Huygens came and said, no, light is having the wave nature. And even though they are from the different centuries, after that the famous Maxwell scientist came and said, don't worry, light is having the particle nature and the wave nature also. Light is having the both properties. Then we are saying the light we are taking in the form of the photons. When the light is falling on the semiconductor material, the electrons are revolving in the last orbit. Because of this light, which is having particle nature and wave nature, because of this energy, the light energy, the electrons are being excited from the last orbit to the out of the atom. They are coming out of the atom. And these electrons we are calling them as free electrons. When more light falls on this, when the more light falls on this semiconductive material, which is cadmium sulfate, which is a photosensitive material, then more number of electrons are coming out of their atoms. And remember, all these electrons are last orbit electrons. They are coming out of the atom. And these electrons, if the more number of electrons are coming from the atoms, then the resistance of this material is decreasing. This is the property of LDR. When more light falls on this photosensitive material, then more electrons are coming out and the resistance is decreasing. This is the property of this LDR. Here, you see, this is the circuit diagram. We have indicated the circuit diagram with two arrows. These two arrows are indicating that light is falling on the LDR. Light is falling on the LDR. This is being indicated with the two arrows. We will also give some casing to avoid the dust and moisture effect. Because if more dust and moisture we observe on this photosensitive material, then the light will not fall on that material. In order to make it free from the dust and moisture, we are covering this material. Sir, then the doubt comes, sir, if we are covering that material, then how light will fall, sir? You are saying that is a photosensitive material, but you are also saying you are covering with a material. When you are covering with this material, then how light falls? That's why we are covering with a transparent material. Means light can enter through that material. But dust and moisture will not affect this LDR. So light can fall. So that is a transparent casing. We are covering with a transparent casing. So light will enter through that transparent casing. But dust and moisture will not affect this LDR. This is how we are using the casing. And when the light is falling, light is nothing but we are discussing photons. So group of photons. So these photons excite the electrons from the last orbit to the out of the atom. Practically, whatever we discussed, now we are discussing with respect to the energy band diagram. This is valence band, this is conduction band. Electrons, the energy levels of the electrons in the last orbit of the semiconductor material we are representing with the valence band. This is the energy band. There is no particular energy band in practically with a rectangular shape, but for our convenience, we are representing the valence band with this rectangular shape. This is the energy of electrons. Sir, the electrons where they are residing? These electrons are residing in the last orbits of the atoms. So the energy levels of the electrons residing in the last orbits of the atom, last orbits of all atoms we are representing with the valence band. And the energy levels of the all electrons that are residing outside of the atoms in the interatomic gaps, we are representing with the conduction band. So when the light falls, then by gaining that light energy, this electron from valence band, this will move to the conduction band. So the electron from valence band, this will move to the conduction band. This will leave a hole here. Hole is a positively charged particle. We already discussed. It is an imaginary particle. We already discussed. So if 4 electrons are moving from the valence band to the conduction band, then we observe 4 holes in the valence band. These are the positively charged particles. The electrons are negatively charged particles. Now we are observing the conductivity due to 2 particles, electrons and holes. These are the positive charge carriers, these are the negative charge carriers. If more number of free charge, both are free charge carriers. If more number of free charge carriers are being observed, then the resistance of the LDR is decreasing. When the resistance of the LDR is decreasing, when more number of free charge carriers are being observed, when we observe more number of free charge carriers, when more light falls on the LDR, so when more light falls on the LDR, then more number of electrons go from the valence band to the conduction band. Because more number of electrons are going from valence band to conduction band, we observe more number of holes in the valence band. Because of that, resistance is decreasing. This is how the light dependent resistor will work. Now we have shown the same thing with the graphical representation. On the x-axis we have taken the illumination, means the light intensity level. On the y-axis we have taken the resistance. If the more illumination means the resistance is decreasing. See, when the light illumination is low, the resistance is high. When the light illumination is increasing, then the resistance is decreasing. See here, the LDR change of the resistance will also depend upon the wavelength of the light. Each light, blue light, VIBGYOR, all lights, violet, indigo, blue, yellow, all these lights are not having the same wavelength. So depending upon the wavelength of the light, the resistance also varies. The same amount of the illumination only falling, but if the color of the light is changing, then also resistance is changing. So the change of the resistance depends upon the wavelength of the light, intensity of the light, how much intensity of the light falling on the LDR, and it also depends upon the band gap. What is the gap between this valence band and conduction band? Means what is the material you are using? Depending upon the material, the band gap will be decided. If the band gap is less, more number of electrons will move from the valence band to conduction band. The resistance easily decreases. If band gap is more, less number of electrons move from the valence band to conduction band. And then doping level. We have already discussed it in the 4th chapter. If we are using heavily doped material means, we are using a very conductive material. So depending upon the doping level also, resistance changes. And the surface area, how much area? You are taking small LDR or you are taking a very big LDR, surface area. And thickness, how much thickness? It is very thin LDR or very thick LDR. All these factors will affect. So when the light falls on the photosensitive material, this is a semiconductor material. When the light falls on this material, the electrons in the last orbit, because the electrons are revolving in the last orbit, they are in the valence orbit, they got the energy. After they got the energy, they will come out of the atom. We are calling these electrons as free electrons. These electrons, they will revolve around the atom. Means around the atom means in the interatomic gaps. These electrons only, the electrons revolving in these interatomic gaps, these free electrons, if the more free electrons are coming, then the resistance is decreasing. So the resistance of this material is being affected by the number of electrons they are coming out of the atom. Similarly, we are having many atoms because we are using the crystal here. It is a photosensitive material. We are using a crystal. When the electrons are coming out of the atom, then the resistance is decreasing. So this is how, when the light falls on this material, When the light falls on this material, the electrons in the last orbit, they will come out of the atom. Now these electrons which are coming out of the atom, these electrons are called as free electrons. If more light falls, then more electrons will come. If more electrons are coming, then the resistance is decreasing. We have discussed the LDR. We are revising. What is LDR means? Light dependent resistor. It is a variable resistor or fixed resistor? LDR is a variable resistor. It is a passive electronic component or active electronic component? Passive electronic component. Means it is capable of storing energy or not? No, it will not store energy. Any resistor, it will not store the energy. Now the resistance of the LDR varies with respect to which factor? Light. Intensity of the light. Where we are using this LDR? We are using for the automatic street light. When sunlight comes automatically, we want all the lights to be turned off. When the sunlight goes, then we want all lights to be turned on automatically. This circuit symbol here, the arrow is representing the intensity of the light. The light is falling on the resistor. That is being indicated with the arrow. What is these curves? What are these curves? Photosensitive material. Which material we are using? Conductor or insulator or semiconductor? Very good. Semiconductor material we are using. Which semiconductor we have discussed? Cadmium sulfide. Below this semiconductor, which material we are using? Insulator. Insulating substrate we are using. Okay. So if more light is falling on this cadmium sulfate, then the resistance of this LDR is low. Very good. If the light, that intensity that is falling on this cadmium sulfate is very less, then the resistance is high. This is simple principle. If more light falls, then the resistance is low. If less light falls, then the resistance is high. The same thing we are representing in a graph. See, when the light illumination is increasing, then the resistance is decreasing. But this is non-linear. Okay? On the x-axis we have seen illumination. On the y-axis we have seen resistance. If more light is falling from the valence band, the electrons are moving to which band? Conduction band. Practically, there are no valence band and conduction bands. For our convenience, we have taken these bands. These are energy bands. Valence band and conduction bands are which bands? The electrons' energy levels we are representing here. Valence band and conduction band. The electrons in the valence band are practically they are the electrons in the last orbit. Electrons in the valence band are last orbit electrons. When these electrons are coming out and they are moving to conduction band means atom, outside the atom, interatomic gaps. When the electrons in valence band, they will move to conduction band. When the electrons in the last orbit, they will come out. When they gain energy. Which energy we are giving now? Light energy. Light in the form of the photons, that energy we are giving here. Then the electrons in the last orbit, they are coming out. So electrons in the valence band, they are moving to the conduction band. For each electron that is moving from valence band to conduction band, there is a hole observed in the valence band. If there are 4 electrons moving from the valence band to conduction band, then 4 holes are observed in the valence band. These are the negative charge carriers, these are the positive charge carriers. Okay, hole is an imaginary particle. Now we are using a insulating cap or casing to avoid dust and moisture. But if we are using a casing around the LDR, how the light will fall on it? That's why we are using a transparent material. We want to shield it from the moisture and the dust, but we don't want the light should be stopped. Light should enter. That's why we are using transparent. When the light is falling on this material, electrons in the last orbit, they are moving to the interatomic gaps. The electrons in the valence band, they are moving to the conduction band. Okay, now we are also mentioning for each light the resistance, is it decreasing in the same manner? No. When the wavelength of the light is changing, then how the light is falling and how much resistance is decreasing, that is also changing. If the same amount of blue light is falling on the LDR and the same amount of yellow light is falling on the LDR, the resistance will not decrease in the same amount. So it will depends upon the wavelength of the light, and it also depends upon the intensity of light, how much light is falling. It also depends upon the band gap of the semiconductor material you are using. If the band gap is less, then more number of electrons easily they will go from valence band to easily the resistance decreases. If the band gap is more, then only less number of electrons will move from valence band to conduction band, and the resistance decrease is only less. And it also depends upon the doping level. If heavily doped semiconductor means easily resistance decreases. If it is lightly doped means the resistance will not decrease easily. Surface area, whether you have taken a tiny LDR or whether you have taken a big LDR. Thickness, thin LDR or very thick LDR. What are the advantages? The cost is very less. With the operation we are doing, it is cost effective and the power it takes is very less. These are the main two advantages. But the disadvantage is, it will not respond immediately. Why it will not respond immediately? Because it is non-linear response, you can see. When we are changing the light, the resistance is being decremented non-linearly. It takes little amount of the time. Immediately when sunlight comes, it will not turn on. It will take little amount of time. Slow response. Next, there is a limited spectral range for all lights. For our entire spectrum, it will not work. For some wavelengths only, it will work. These are some of the disadvantages. So we have discussed LDR and how we have constructed the LDR and how its resistance is being affected, and we have seen advantages and disadvantages.